Hey everyone. So today I'm going to talk about Ramsey's theorem, which is a theorem in graph theory or in combinatorics. And we're going to talk about the finite version and the infinite version, prove both, and then make some remarks about the interplay between the finite and the infinite in mathematics. So Ramsey's theorem starts with a party trick. Suppose that 6 people show up to a party. And we suppose for simplicity that all these 6 people are either friends or strangers. So between every 2 people, you're either already friends or you're meeting for the first time. Then the theorem says there always exists 3 people that are all mutual friends or mutual strangers. So those 3 people, we're going to call that a triangle, where it's 3 people that are all mutual friends or all mutual strangers. So for example, if everyone at the party was meeting for the first time, then any 3 people would form that triangle. If everyone was already friends, then also any 3 people would form that triangle. But the theorem says that for no matter what combination you have of friends and strangers going in, you can always find a triangle somewhere. So here's how we prove the theorem. We're going to start with a graph and represent the people as vertices. So maybe we call them 0 through 5. And then we're going to color the graph with red and blue. A red edge will indicate that those 2 people are friends, and a blue edge will indicate that those 2 people are strangers. So for example, maybe 0 and 1, they're strangers. 0 and 2, maybe they're friends. 0 to 3, maybe they're strangers. Say it's also the same for 0 and 4. And then maybe 0 and 5 are friends. And also for everyone else, but I'm not going to draw it. We'll just focus on 0. So it's some combination of friends and strangers. This is just an example. So starting from 0, we note that there must be 3 edges coming out from 0 that are all the same color. And it has to be at least 3, because if it was just 2 friends and 2 strangers, well then you'd be summing to 4, and where's the 5th person? So because there's 5 other people, there must be at least 3 of those people that are either all friends or 3 of those people that are all strangers to person number 0. So in this example, here 1, 3, and 4 are all strangers to person 0. So now we haven't completed a triangle yet. These are just all the same color coming out from 0. We need a triangle where it's 3 people in a triangle. So there's 2 cases. Case 1 is that any of the people 1, 3, and 4 are strangers. So if any of these people are strangers, then you get a triangle between those 2 people and then the people we know are strangers, 0, 1, 0, 3, and 0, 4. So if these 2 strangers, or if these 2 people were strangers 1 and 3, then it'd be 0, 1, and 3 forming a triangle. If it was 3 and 4, it would be 0, 3, and 4 forming a triangle, and so on. So then those 2 people and 0 form a triangle. So we're done in case 1. So what about case 2? Well, case 2 is just not case 1. So if none of these are strangers, then they're all friends. So case 2 is that all of 1, 3, and 4 are friends. Then they form a triangle. And again, we're done in case 2. So depending on the relationship between 1, 3, and 4, we may get the triangle of friends, we may get the triangle of strangers, including 0. But this is how you prove the theorem. And we note that it was necessary to have 6 people total, because if you didn't start with 6 and only started with 5, then the first step of this argument wouldn't work. So if you only had 5 people, maybe we took out 4, you might only have 2 friends and 2 strangers coming out from 0, and that by itself doesn't mean the theorem is false, but it means the proof doesn't work. And actually, you can show that 5 people don't work. So just down here, we'll do a quick note. 5 people don't work. Or the theorem doesn't work for 5 people. And the quick example you can draw, let's just assume all these people are strangers and all these people are friends. And you can check that this graph down here, there's no triangles of the same color in this graph of 5 people. So you need at least 6 people for this property to hold, where there's always 3 people that are mutual friends or mutual strangers. Okay, so we've proven Ramsey's theorem for this party trick, and now I'm going to state the more general finite Ramsey's theorem. So finite Ramsey's theorem is the following statement. For all n, so that's some natural number n, there exists another number r of n, that's the Ramsey number for n, such that any complete two-colored graph of at least size r of n has a complete monochromatic subgraph of size n. And just some terminology, by complete, we just mean every possible edge has been drawn. Two-colored, just like this example, everything is either red or blue. And then the monochromatic subgraph, in the party trick example, we had a monochromatic subgraph of size 3. Monochromatic just means everything is the same color. So, for example, we showed that r of 3 is equal to 6. So if you're looking for a triangle, or you're looking for a monochromatic subgraph of size 3, you need at least 6 people, or 6 vertices in the graph to guarantee that. So this proof here showed the number was at most 6, but because we have a counterexample where 5 doesn't work, that shows the number is exactly 6. It takes a bit more work to show, but r of 4 turns out to be 18. And this is a bit more tricky. You don't have a quick argument like this. It takes a lot of work to show this. But the finite Ramsey's theorem states that there's always some number for any subgraph size. So if you want a graph of size 5, there's some number out there where any graph at least that size will give you a monochromatic subgraph of size 5. So that's the finite Ramsey's theorem. And then this also has an extension to the infinite. So infinite Ramsey's theorem that states that for every infinite complete two-colored graph, there exists an infinite complete monochromatic subgraph. So in other words, what we're saying is that the Ramsey number for infinity is infinity. I'm putting this in quotes because this is kind of nonsense. More precisely, we're saying the Ramsey number for Aleph naught is equal to Aleph naught. That's the size of a countably infinite set. So every countably infinite graph, or bigger than that, but at least size countably infinite, has a countably infinite complete monochromatic subgraph. And by the way, this works for more than two colors. For any finite number of colors, these theorems are true. And they're even true for hypergraphs. And a hypergraph is just a more general notion where these graphs have one edge between two vertices, but a hypergraph has hyper edges between collections of more than two vertices. So maybe a 3 hypergraph, your edges are collections of 3 vertices. So even in that more general context, both the finite and infinite Ramsey's theorems hold true. So just to give some examples of infinite graphs, you might have just a long stick like this. Where that goes on forever. Maybe all of these edges are red. And then every edge that I'm not drawing is blue. And so on. Another example of an infinite graph, maybe your stick doesn't go up forever, but you just get longer and longer sticks. Oh, sorry, these should have been red. You just get longer and longer sticks coming out from some central root. So here, all of these edges are red, and then every edge that I'm not drawing is blue. So all of these are blue. So here are some examples of infinite graphs, and then you might be able to see what the infinite complete monochromatic subgraphs look like. So in this example down here, we don't have enough red edges, so just take every other vertex, and then all of these will be connected by blue edges. And for here, it's the same story, only we have a lot more options. Maybe you can take all of the vertices down here, and then this entire row is all connected by blue edges as well. So this would be your infinite monochromatic complete subgraph. So what we're going to do next is we're going to prove the infinite Ramsey's theorem. And the proof of infinite Ramsey's theorem is actually sort of like the proof of this party trick, only things are infinite, and instead of having these cases at the end, you just kind of go forever with an infinite recursion. But the proof is not that hard, and then we're going to use both the proof and the statement of infinite Ramsey's theorem to derive the finite Ramsey's theorem in 2 different ways. So that's what we're going to do next. So now we're going to move to the proof of infinite Ramsey's theorem. Let's move this over. So proof of infinite Ramsey. So we're going to start with an infinite complete 2-colored graph. And we're just going to call that G0. And just like the proof of the finite case, we're going to pick any A0 inside of G0. And then we're going to look at the rest of G. So the picture looks like this. You started with some big graph G0, and then you picked out any element, any vertex A0. So over here, we have the rest of G0. So that's G0 with A0 removed. So A0 has a bunch of red edges and a bunch of blue edges. So maybe all of these are red. So everything down here, maybe we skip a couple. and then everything else is blue. Or something like that. Maybe it alternates forever. Maybe you get another, red edge every now and again or something like that. So G0 was infinite. So if we remove just one thing, this graph stays infinite. So there are infinitely many edges coming out from A0. So remember the proof of the party trick, you had 5 things coming out from one person. We said at least 3 of them must be the same color. Well, here we have infinitely many things coming out from A0, so infinitely many of them must be the same color. So infinitely many edges from A0 to the infinite rest of G0 must be the same color. If not, then you'd have finitely many red edges plus finitely many blue edges to get finitely many edges total, but you have infinitely many edges coming out. So there must be an infinite collection that are all the same color. So let G1 be the vertices in G0 minus A0 that share that common color to A0. So in this case, the way I drew it, I wanted this set here to be infinite. So maybe down here we have a whole bunch of blue edges. We call that G1. So we started with A0, the rest of G0 was infinite, and then we found an infinite subset such that everything out from A0 had the same color. So G1 is infinite. And so now we repeat inside of G1. So we pick A1 inside of G1. So this right here, maybe that is A1. And then we look at all the edges just inside of G1. So maybe this time you have a couple reds coming out, you have a couple blues coming out, and then maybe everything else is red this time. So G1 was chosen in this case such that everything from A0 to G1 was blue, but then inside of G1 it has all sorts of different colors maybe. So we pick A1 in G1, we look at the edges coming out from A1 in G1, and then we find G2 sitting inside of G1, and infinite subgraph such that A1 has the same colored edge to all of G2. And then we just keep repeating that forever. So by recursion, we define both AN and GN for all natural numbers n, such that a few things hold. We want all of the GNs to be infinite. And this is needed just as part of the recursion to make sure we can keep it going. AN is always inside of GN. The GNs form a descending chain. So descending chain of subsets. And finally, AI, or I'll use N, AN has the same color edge to all of Gn plus 1. So we're continually nesting down, picking an element, and finding some edge or some color where it's the same color edge to all of an infinite subgraph of the next gn. So this is the recursion, and we define all these things. And now we're almost done with the proof. We just need to figure out how to use these ANs to get a monochromatic subgraph. So proof of infinite Ramseys continued. So let's look at the ANs we defined. We have A0, A1, A2. I'll just draw a few more, and so on. And we're not done yet, because in this example, we had that A0 had a blue edge to the infinite set G1. So everything ahead of A0 was blue, because all of these, well, A1 was chosen in G1, A2 was chosen in G2, but they form a descending chain. So everything we chose ahead of A1 is also in G1, which means A0 has a blue edge to all of these. So A0 has a blue edge to everything ahead of it. Likewise, in the example, A1 had a red edge to everything ahead of it. Maybe A2 also has a red edge to everything ahead of it. Maybe A3 goes back to blue. A4 goes back to red. So every AN has an edge of some fixed color. Maybe we'll call it Cn. So Cn is either red or blue, to a m for all m bigger than n. But the colors might be alternating. So now we just need one more trick. We just need to use the same kind of argument that finite plus finite cannot be infinite, and strip this down to a subsequence where it's all the same color. So just choose a subsequence. We'll call that n sub I for I in n, where Cni is all one color. So again, Cn's, we're just marking what these colors were. And because there's an infinite number of Cn's, but it's only choosing between red and blue, there must be an infinite subsequence such that that's all the same color. So then the sequence ANI for I in n will all have edges of that same color. So maybe it's the reds that show up forever. So in this case, we're taking these two, we're taking this one, and then we're taking anything else that has a red edge to everything ahead of it. So there's infinitely many of these. They all have red edges to infinitely, or to everything ahead of it. So that will give us our monochromatic complete subgraph. So that there is the end of the proof of infinite Ramsey's theorem. So now that we've proven the infinite Ramsey's theorem, we're going to give a proof sketch of the finite Ramsey's theorem. And the sketch will be nearly complete. I just don't want to write out all the details because actually you don't really need to see all the details. I think it's pretty clear, why the proof will work. So I'm going to move this aside, but I'm going to put this here, and we'll just be switching out these two pages a few times. But here's the proof idea for finite Ramsey. And it's going to be inspired by the infinite proof. So we want to mimic the proof for infinite Ramsey. At the end of the proof of infinite Ramsey, we had this long sequence of ANs, and then we found a subsequence such that it was all the same color looking at the vertices going forward. So if we only want a monochromatic subset of some finite size, then this only had to be a long enough finite sequence. So if we fix n and are looking for a monochromatic subgraph of size n, we need the ANs to have length, as a sequence, length 2n. So in other words, n is going to range from 0 to 2n minus 1, right? 0 index, so minus 1. And that's because if these have length 2n, then there must be at least n of them such that the color looking forward is all red or all blue. So here it was finite plus finite can't be infinite, and here it's something less than n plus something less than n can't be size 2n. So we need the sequence of ANs for this to work in the finite case for Ramsey n to be length 2n. So our recursion needs to run, we start with 0, so 2n minus 1 steps. So now let's take this out, let's put this back, because this down here was our recursion. Our strategy was that we had some, in this case it was infinite graph, we picked one thing out, and then we argued there must be an infinite subgraph such that everything was the same color to the one thing we picked out. So if these were finite, then remember the case with 5 things. If there were 5 things, then at least 3 of them must be the same color, because you can't have 2 plus 2 add to 5. So in worst case, we cut the graph in half. So the size, so I guess I'll say starting from G0, we would choose A0 in G0. Then we get G1 such that the size of G1 is at most, at least we start from G0, we subtracted 1 because we pulled out A0, and then we cut it in half. And we don't need to worry about whether this is a whole number because remember for 5, 5 divided by 2 is 2.5, but then you get 3 things. So whatever whole number size this is, it's at least this here. And we can rewrite this like this. So then inside of G1, as long as that's non-empty, you can choose one thing from it and keep going. So then G2 has size at least G1 over 2 minus 1/2. And we substitute in this is at least size G0 over 2 minus 1/2 divided by 2 minus 1/2, which is G0 over 4 minus 1/4 minus 1/2. So you can see this pattern. In general, Gn will have size at least G0 over 2 to the n, minus 1 over 2 to the n, minus 1 over 2 to the n minus 1, minus 1/2. This is a geometric series. It sums to 1 in the limit. So this is a most size G0 over 2 to the n minus 1. So to guarantee that G to the 2n minus 1, capital N, is non-empty, right? That's what we need to choose that last step to get this sequence of ANs length 2 to the n, length 2 capital N. We need that G0 divided by 2 to the 2n minus 1 is greater than 0. So that gives us a starting graph size. G0 is strictly bigger than, put this over here, where we add 1, we multiply over, 2 to the 2n minus 1. So that's all we need for this graph to be strictly bigger than this size, and then we can run the recursion. We do the same recursion we did here for 2 to the n minus 1 steps. Then we get an's. We get this sequence of an's that is length 2 to the 2n, and then half of that must have the same color looking forward. And then we get our monochromatic subgraph of size n. So the same proof we did here works. We just have to start with a graph of at least this size. So in other words, the Ramsey number for n is bounded above by some finite value, 2 to the 2n minus 1 plus 1, so that it's strict. So this isn't the proof, this is the discovery of the proof. But then the same recursion we did in the infinite case will run in the finite case. So that's how you can kind of discover the proof of a theorem about finite objects by studying the proof of a theorem for infinite objects. So I'm not like shadow boxing against any finitists here, or maybe I am a little bit, but even if you think that infinite objects are not useful in the real world because maybe they don't exist in the real world, and even if you think that mathematical objects should only be finite, the fact stands that this infinite proof, even if it was just formal nonsense, was a useful heuristic to discover the finite proof. So now I've learned something about the finite world by thinking about the infinite world. And I think that's a very profound correspondence. Okay, so now we have proven finite Ramsey's theorem directly as inspired by infinite Ramsey's theorem. But what we're going to do next is show how the infinite Ramsey's theorem can actually directly imply finite Ramsey's theorem without reproving it. So that's what we're going to do next. We need a new piece of paper for that. So proving finite Ramsey directly from infinite Ramsey. And there's more than one way to do this, but the way that I'm most fond of uses model theory and first order logic. So this is a great kind of introduction to what first order logic and model theory looks like. It's actually pretty rare to find direct applications of model theory to important theorems like this, so it's a pretty fun example. So what we're going to do is, given infinite Ramsey's theorem, which we proved, we will assume finite Ramsey is false and get a contradiction. So again, we're going to be fixing that n, and suppose there is no Ramsey number. R of n. So for bigger and bigger graphs, or I'll say for bigger and bigger sizes, k, there is a graph of size at least k with no complete monochromatic subgraph of size n. So it's like you get bigger and bigger counterexamples to Ramsey's theorem for size n, and that shows that there's no size where beyond that you'll always find the monochromatic subgraph. And we're going to get a contradiction by building an infinite graph such that the infinite graph also does not have a monochromatic subgraph of size n, but that contradicts the infinite Ramsey's theorem that shows that every infinite complete two-color graph has an infinite monochromatic subgraph. So for this, we're going to need to step into first-order logic, and I like to think of this like, opening up the hood of the car or taking a look at the source code, where we're really going to get into the nuts and bolts of what's going on inside of math in order to prove this. So it's a really cool application. So we're going to fix our language. We use a script L. Our language inside of first order logic will consist of two relation symbols, color red and color blue. So these are two binary relations. Symbols. And the domain of discourse here is vertices in a graph. So our domain is vertices in a graph. And what I mean by this isn't really standard terminology here, but just in terms of first order logic, we can only talk about one thing at a time. So in this case, the symbols, the variables in the formulas we write down will only refer to vertices in a graph, and we'll use these relation symbols to denote their color. So if V and W are vertices, the color red VW, this is either going to be true or false. So it's true if the color is red, it's false if the color is not red. And actually, we didn't even need to have this second relation symbol because this is already one or the other, true or false. So if the color red is false, we could just say it's blue. But for the purpose of just writing down some more first order logic as an example, we're just going to have two relation symbols and then an axiom that states that the color is either red or blue and not both. So actually, let's write that axiom down now. So we're going to call that axiom, let's just use a phi. So phi is going to be the axiom that states that all edges are blue or red and not both. So this is, again, we're trying to enter a theory of a complete two-colored graph. So all edges, well, that means it's a pair of vertices that are not the same. So for all V and W, either V equals W, or, this is the symbol for or, I just realized the symbol for or is the same as the symbol for V, so that is not so good. I'm just going to change the V to an X. So for all X and W, so I won't use any V's to avoid confusion. For all X and W, either X is the same as W, or the color red is true for XW, or the color blue is true for XW. So this means it has some color, and this is the symbol for and, it is not, symbol for not, and it is not the case that the color is red and the color is blue. So if you've never done first order logic before, this looks really hideous. You just get used to writing stuff like this down. So here we have or, and, this is not, here we have another and, here we have an or, and this is for all. So again, in normal math, you maybe have used the upside down A as shorthand for writing out for all, but in here it's the other way around. This is not shorthand, this is a logical symbol, and for all is not a symbol in first order logic. So we're not writing out an English proof here, we're writing out a string of symbols that could be computer verified. So that's the restriction on first order logic. And then the variables, they can't be numbers, they can't be sequences, they can't be sets. They have to be the domain of discourse of your first order theory. So in this case, they're only vertices in a graph, not even the edges, just the vertices. So this first order formula says that all edges are blue or red and not both. And again, we're trying to capture our assumption up here, which was our assumption that's going to give us a contradiction. So we have all edges are blue and red and not both, so it's a two-colored graph. And we need to capture bigger sizes k. So let phi k, for some k, this is the formula that the graph has size at least k. So how do we write this down in first order logic? This is something we don't need any specific relation symbols for. We can just use equality. So there exists some x0 through xk minus 1. And we need to declare all of these are distinct. So we're going to use a big and. So for all I not equal to j, xi does not equal xj. So this is a big and. So it's like shorthand for writing out a very long formal sequence where you had a bunch of ands, and then the i's and the j's would go from 0 all the way through k minus 1. And just as a quick note here, I'm indexing these variables by numbers. So really, I'm describing a scheme for writing out a first order sentence in some higher meta theory. So you can't actually index over k or even these like ... dots. These are illegal in first order logic. So what I'm saying is that you could write out a first order formula following this scheme, but the scheme is described in the meta theory. So there's this interplay between target theory and meta theory, and it's just something you have to watch out for when you're first studying this stuff. So anyway, we have a formula that states that the graph has size at least k for every k. Note there is no formula that says the graph is infinite because you would have to quantify over k or have a formula that was infinitely long. But both of those things are illegal in first order logic. So we have a formula phi says all edges are red or blue, not both. Formula phi of k, the graph has size at least k. And then we need that there's no monochromatic subgraph of size n. So I'm going to call that psi. So psi is the formula. There is no monochromatic subgraph of size n. And unfortunately, I'm out of room on that page. Just have to grab another page. So continued. So psi can be written formally as saying that for any choice of x0 up to xn minus 1, so capital N choices of vertices from the graph, that one of the edges is red and one of the edges is blue. So this time we have a big or, I does not equal j. One of the edges, xi, xj, is red, and one of the edges, big or, has color blue. So here this is a big or. So again, first order formula, or at least a scheme for how you would hypothetically write down a very long first order formula if you were told exactly what capital N was. So now we're going to take all these sentences and put them together into a theory. So a theory is a collection of sentences. So we start with phi. That said all your edges were red and blue, not both. We're going to throw in psi. And psi said that you did not have a monochromatic subgraph of size n. And then we're going to throw in phi 0, phi 1, phi 2, phi 3, and so on. So this is an infinite theory. It's an infinite collection of first order formulae. And this is, again, perfectly legal because we're describing this in the meta theory. So in the meta theory, you can use ... You can quantify over k and have sequences and all that fun stuff. But every one of these formulas we're defining is some concrete first order formula just with the allowed symbols. And I'm emphasizing all of these strict rules because you need to have a first order theory in order to apply really powerful theorems to it. So one theorem we're going to use, which is the compactness theorem, is that if T is a first order theory, such that every finite subset has a model, then T, oops, then T has a model. And I'm not going to define what model is, but it's kind of what you expect. It's just some concrete mathematical structure, in this case a two-colored graph, where this sentence is actually true. So to model a sentence or a finite number of sentences, all of those sentences need to be true. And same for an infinite number of sentences, every single one of those infinite number of sentences needs to be true. And so by assumption, we have graphs. I'm just going to use maybe H. So HK, such that the size of HK is at least K, with no monochromatic subgraph of size n. With no monochromatic subgraph of size n. So they're two-colored graphs. Maybe I should have said two-colored complete graphs. So that means that HK, it models or satisfies the formula phi. That said that all edges were blue and red or not both. You're two-colored. That's by assumption. So HK satisfies phi. HK also satisfies psi. Psi says there's no monochromatic subgraph of size n. And HK has size at least, this makes no sense. It's a finite graph of size k. So we want to prove that, size k doesn't work, so there's a graph of size k that doesn't work. So if you have size k, then that means I model the formulae that say you have at least size everything up through k. So it models phi 0, HK models phi 1, and HK models phi k. So it has size at least 0, at least 1, and it has size at least k, actually exactly k. So we have these two-colored graphs. They're finite, and they have no monochromatic subgraph of size n. Actually, we could have said greater than or equal to down here before. That's actually what I meant to write, but it's fine. So the point is, HK will model the first, I guess it's, 2 plus k plus 1 sentences in T. So any finite subset of T you choose, for large enough k, HK will model that. So for any finite T prime in T, there exists k, and here I'm in the meta theory, I'm just using it for shorthand, but there is some k such that HK models T prime. So some k, and actually I don't like that, I'm not going to mix up meta theory and target theory. I'll just say there is k. There is a k such that HK models T prime. So the hypothesis of the compactness theorem that every finite subset of T prime has a model, even if the model keeps changing, that's okay. By the compactness theorem, T has a model. H. So H models all of T. But think about what T is describing. We're saying that you're a two-colored graph. You have no monochromatic subgraph of size capital N. You've size at least 0, size at least 1, size at least 2, size at least 3 for bigger and bigger sizes. But then H is infinite with no monochromatic subgraph. Of size n. And this is a contradiction. So we get a contradiction right there at the end because we prove for infinite Ramsey, every infinite two-color complete graph has an infinite monochromatic subgraph, but H is a graph without even a monochromatic subgraph of size capital N. So this is a contradiction. It contradicts infinite Ramsey, so this assumption must have been false. If this assumption is false, then capital N does have a Ramsey number where you run out of these HKs, and eventually every graph of size bigger than R of N will have a monochromatic subgraph of size N. So I think this is a pretty cool application of the compactness theorem and first order logic to prove something we're actually interested in finite graph theory. And there's a couple notes I want to make here. So the first note is that the contradiction at the end felt too strong. So what I mean by that, we contradicted the subgraph, or having no monochromatic subgraph of size capital N, because we know it has an infinite monochromatic subgraph of size, or an infinite monochromatic subgraph, let alone one of size N. And I think that the heart of that, too strong contradiction is the fact that finite Ramsey didn't require any axiom of choice. But if you think about the proof of infinite Ramsey, it actually needed a little bit of the axiom of choice because we do make infinitely many choices. So we were proving a weaker result from a stronger result. I think that's why the contradiction at the end sort of blew it out of the water. So that's one note. Another note is that this is a proof by contradiction, so we don't actually know what R of N is. Whereas the proof that we gave before of finite Ramsey, that proof gave some bound, 2 to the 2n minus 1 plus 1. And you can actually get much better bounds than that if you sort of scrutinize the proof and tighten the screws a little bit. But in this case, we did not get a bound. I think that's also because we're using these high-powered compactness theorems, and infinite Ramsey, again, was proven with a little bit of the axiom of choice. So this is a pretty cool application of the compactness theorem. And if you dig into the proof of the compactness theorem, there's a few different ways to prove this. And one way to prove that is to actually build the model you're looking for from all the finite models. And so there's a couple ways to prove compactness. So you could actually sort of take out all of the first order logic from this contradiction proof and just directly build the contradictory graph H from the graphs HK. And you wouldn't have any first order logic. You would just be directly building H from HK. But that construction, one construction I know of that does the trick is called an ultra product. And that's getting pretty advanced. You need to introduce the notion of an ultra filter. So it's not something I wanted to do for this talk. But anyway, that's all I had to say. I think it's a pretty cool interplay between the infinite and the finite, how we can use compactness as a bridge to go from an infinite theorem to a finite theorem. Sometimes the bridge goes one way, sometimes it takes you the other way. But Ramsey's theorem is just a really nice sort of fertile ground for seeing all this different interplay between the infinite and the finite.